So, although it's written on my first slide that this talk is in honor of Jerry Geralnik, of course it's really I who feel honored at having been invited to speak amongst such a distinguished panel of guests. So my talk will be, I'm going to try to review some of the really spectacular progress that we've seen over the past 5 or 6 years in scattering amplitudes, particularly in non-abelian gauge theory, Yang-Mills theory. And I hope that most of my talk will stay at a comfortable cruising altitude, although inevitably bits and pieces of it may dip down into formulas. But on the whole, I'll try to give a bird's eye talk, bird's eye view of the situation. And this subject has been developed by a large number of individuals. I guess it was spearheaded in a very influential paper Ed Witten wrote 6 years ago, which I will review in my talk. And since then, it has been pushed forward by many, many people, several of whom are listed on this slide, and that I have had the great pleasure of collaborating with. Actually, it occurred to me that if you include the 2 experimental papers I wrote as an undergraduate, this is a set of measure 0 in my space of, in my list of collaborators. I guess that's, even though I only had 1 or 2 experimental papers, I guess that's an example of the Malmquist bias. So let me first begin by telling you the statement of the problem. You know, what is it that this line of research that I'm going to describe is aiming to do? And the goals of the program are, first of all, to explore the rich mathematical structure of scattering amplitudes. And I should emphasize that this structure has been hidden in traditional methods that we've all known about for many years or learned in textbooks. And it's only much of it has only come to light in recent years. And furthermore, you know, sure, mathematical structure is great and all that, but we'd like to exploit that hidden structure to make previously impossible calculations trivial. And sometimes I hesitate a little bit to put the word trivial on the slide because, you know, maybe it's kind of strong and maybe it's presumptuous for such a young person to be saying something so bold. But it really is the case that the progress over the past 5 or 6 years, has made previously impossible calculations trivial. In fact, one of the stories I like to tell is about a PRL paper we had about 4 years ago that 6 months before we wrote it would have been the calculation would have been impossible to do by any method. But 6 months after we wrote it, it never would have been accepted to PRL because it was so trivial by then. And I was reflecting on this during Jerry's talk when I was thinking about what a testament it is to have a nearly 50-year-old PRL that's still still in its prime. So, and perhaps someone who's more senior than me might be able to mumble some more grandiose words about this research program, something along the lines that we're looking for some new ways of thinking about quantum field theories, completely new ways to formulate how we think about quantum field theory. So on that note, let me say a little bit about Lagrangians. Of course, for most of us, well, I think for almost all of us, Lagrangians are how we first learn about quantum field theories, and they have many important uses, several of which Jerry has worked on throughout his career. Well, I should have obviously put, but when you're interested in scattering amplitudes, especially for theories with spin, that is for gluons or for gravitons, the Lagrangian formulation brings with it a lot of unnecessary and undesired encumbrances. For example, they require you to introduce a lot of garbage. And what I mean by garbage is gauge symmetry. So we're often taught that we should think of gauge symmetry as some beautiful, deep, and really mathematically beautiful principle. And it is. But if you think about it, really, it means you're introducing garbage into your path integral. It means that the physics you're interested in is only a tiny subset of what's living there in your path integral, and almost all of this structure that you've built up lives only to cancel out other stuff. You have to worry about gauge fixing. When you do loop calculations, you have to worry about ghosts. You have a lot of gauge redundancy in individual Feynman diagrams, which you know only cancels out at the end of the day when you add together all Feynman diagrams. So that's what I mean by when I say that Lagrangians contain a lot of garbage. And furthermore, as I will explain or review, Lagrangians often obscure simplicity and occasionally even hidden symmetry of scattering amplitudes. If you think about it for a minute, the S matrix, by its very definition, should depend only on initial and final conditions which you set in the infinitely far past and the infinitely far future. However, the traditional mechanisms for calculating any S matrix element require an enormous amount of auxiliary machinery, namely space-time. You have to introduce a concept of a local field, and then you have to introduce local time-ordered correlation functions, and then you go through a complicated procedure to show that if you calculate, certain singularities of a particular time-ordered correlation function, then magically you can pick off a particular piece of it. You can pick off the S matrix element and prove that that little piece has all the properties you want. Locality, unitarity, gauge invariance, etc. But wouldn't it be nice to have a formulation for calculating S matrix elements that didn't require introducing all of this baggage in the first place? Now, many of you have probably heard these words before. They've been uttered for a very long time. In fact, during Jerry's talk, he said that this paradigm, which was known as S-matrix theory, was king for a while in the high-energy theory community. And the current philosophy is exactly the philosophy of the old S-matrix theory. The only thing I can add, well, the most important distinction, so even though the philosophy of the current way of thinking about it is exactly the same as that philosophy, we have a lot of benefits. We have a lot of new results compared to what we had many decades ago that allow us to make further progress. And so I've written here that if we've been able to see anything more clearly than the giants did back then, it's only because we're staring firmly at the grass right in front of our feet rather than looking at the looming mountains ahead. And let me explain to you what I mean by that. I mean that most of the modern advances are in the particular quantum field theory describing massless vector particles, or Yang-Mills theory. Now, as many people, in particular Chungi, often like to remind me, and in fact Jerry reminded us during his talk today, there are no interacting massless vector particles in the S matrix of our universe. Okay? In the real world, we don't see such things. The SU3 gauge particles, known as gluons, they don't appear in the S matrix because of confinement, related to a result which I should point out has already received its Nobel Prize. The SU2 gauge particles, the W and the Z, of course, don't fall in this category because they're massive due to the Beck mechanism. Nevertheless, I should say, of course, the study and computation of these scattering amplitudes is important both conceptually and